Hi, my name is Usama Saqib. I'm a PhD fellow at Aalborg University, Denmark. In today's presentation, I will discuss my conference paper that was accepted at USIPCO 2019 that happened in La Coruña, Spain. The title of this presentation, as well as my paper, is Sound-Based Distance Estimation for Indoor Navigation in the Presence of Ego Noise. Before we begin, this is the agenda of today's presentation. I will begin by giving you a very short introduction of what the aims and objectives of this research is about, followed by the approach that we are taking, and then I will discuss the signal model and problem formulation, followed by the experimental results, and then I will conclude the presentation. The aim of this research is to introduce a model-based approach to time of arrival estimation that could be implemented on any robotic platform or drones platform for room geometry estimation using the concept of echolocation. But the question is, why are we interested in applying echolocation on a robotic platform? Well, an off-the-shelf drone or robot comes with a variety of different sensors that are used concurrently to avoid collision with wall or any objects. However, these sensors are unidirectional and offer limited field of view, which gives limited spatial awareness that can result in a platform colliding with obstacles. Therefore, in order to increase a platform's spatial awareness, we will require incorporating multiple sensors. But we see in nature that animals tend to use sound to make sense of their environment, and they use echolocation to make sense of their environment. Therefore, we are also interested in applying echolocation on a robotic platform so that a robot can estimate room geometry. In literature, we tend to see that two different approaches are taken to localize a sound source: a passive approach and an active approach. In passive approach, localization of sound source is done when the sound sources are externally located. So if we imagine a factory floor with lots of machines generating sound, or imagine a conference scenario with lots of human speakers, and the task of our algorithm is to track and localize these individual sound sources. The advantage of this method is that it is non-intrusive. The disadvantage is that unlike visual landmark, sound has a period of inactivity. So using sound as landmark for localization is an ineffective method. Therefore, for room geometry estimation, passive approach is not feasible. In active approach, however, you probe the environment with a known sound source and you wait for the reflected signals, which gives you important information about the geometry of the room. The advantage of this approach uh, is that it increases localization accuracy, since we are probing the environment with a known sound. The disadvantage of this method is that it is intrusive, but for our application, where we are interested in applying echolocation or active approach on a moving robotic platform, and these moving robotic platforms are always accompanied by ego noise, that is the noise generated by the rotors. Therefore, active approach is a feasible alternative to room geometry estimation. With this in mind, we propose incorporating a loudspeaker and a microphone on a commercial robotic platform, in this case, a drone platform, as shown in the figure. Our system will emit a known sound into the environment and, and record the reflected sound, which will be used to estimate the time it takes for the reflected signal to reach the microphone. Our proposed method will offer a drone 360-degree of spatial awareness and will help in the development of sound-based collision avoidance system. In literature, time of arrival estimation is normally um, estimated by first estimating the room impulse response of the environment and then using peak peaking algorithm to extract time of arrival estimate to extract time of arrival of the reflected signal. The room impulse response is the transfer function between the sound source and the microphone. The general structure of an estimated room impulse response is as shown. Three main components are present within a room impulse response. The direct path component, which is the shortest distance a sound can take. The first order early reflection, which is the distance the sound takes when it bounces off a wall and then reaches a microphone. And finally, the late reverberation. Now, with this in mind, we propose using a model of early reflection that will be generated and then subtracted from the observed signal to retrieve time of arrival of the earth reflection. To do this, we are using a nonlinear least square estimator. And this nonlinear least square estimator is proposed for TOA estimation. And that is because we have the prior knowledge of the known signal that we probe into the environment. So for our setup, we are using a co-located microphone loudspeaker arrangement, and this arrangement will be used to test and evaluate the proposed solution. As stated earlier, first order early reflection is sufficient for room geometry estimation because it gives you the knowledge or the distance between the microphone, sound source, and the acoustic reflectors. In our case, the acoustic reflector is the wall. Now consider a setup where a single loudspeaker is situated in the room that emits or probe a known signal into the environment. This reflected signal is then recorded by a single microphone. The observed signal recorded by the microphone is expressed mathematically by equation 1, where S of n is the known sound source convolved with h of n, that is the room impulse response or the transfer function of the room impulse response in the presence of an additive white Gaussian noise, and additive white Gaussian noise is represented as V of n. As we already discussed in the previous slide, an observed signal is composed of different components: direct path component, first order early reflection, and late reverberation. Therefore, we can express these individual components mathematically as shown in equation 2. So, a reflected sound is nothing but a delayed and attenuated version of the original sound that was probed from the loudspeaker into the environment. Therefore, we can express this delay and attenuation as a first order FIR filter, as shown in equation 3. Now, according to literature, first order early reflection gives us all the information about the geometry of the room, and our interest is to estimate room geometry. Therefore, uh, by, by estimating the position of the reflectors or the first order early reflection, we can find the distance between the robotic platform and the acoustic reflector, that is the wall. Since we are fixing the location of the loudspeaker and microphone, or in other words, since we know where the loudspeaker and the microphone will be positioned on a drone platform or robotic platform, therefore the distance between the loudspeaker and the microphone will be known. This also means that we can estimate the time of arrival of the direct path component offline using an anechoic chamber, or we can estimate it analytically. However, as we discussed earlier, direct path component is not of interest to us in this research because our focus is estimating the time of arrival of the reflected signal, which gives information about the geometry of the room. Therefore, we are interested in estimating the first order early reflection, which gives information about the position of the reflector, such as that is our wall. Therefore, in this equation, in equation 5, we are starting with Q equals to 2. Q equals 1 will be the direct path component. If we take n samples of our observed signals and we also know the model of our source signal, then we can formulate a nonlinear least square estimator as shown in equation 6. This nonlinear least square estimator will be equal to a maximum likelihood estimator when the noise is white Gaussian. So by minimizing the cost function, as you see, we can calculate the gain or the attenuation and the delay associated to the reflection order. In order to estimate the time of arrival and the attenuation or the gain of the reflected signal, we can convert the signal into its frequency domain for effective processing, as shown in equation 9. That is, when the noise is white Gaussian, the maximum likelihood estimator can also be written as 9 in the frequency domain. Now, the previous estimator that I showed should have optimal performance when estimating the gain or the attenuation and the delay or the time of arrival in the presence of additive white Gaussian noise. But this is computationally expensive when computing multiple time of arrivals for the art component, as it will require a multi-dimensional search. To overcome this complexity, a relaxed procedure was implemented, which was originally proposed by Jean Lee and Peter Stoiker. Again, we work with the modified signal where the direct path component is subtracted from the observed signal. As you can see, this is denoted by Y bar. By solving this equation as in equation 10, previous equation, we can derive the expression for gain as shown in equation 11 and the time of arrival as shown in equation 12, where tau is estimated by finding the maximum value of the real part of the observed signal that has been delayed. Now that being said, um, this is the in this experimental setup, we have evaluated our proposed solution in a simulated environment that was obtained by MC Room Sim. The the performance measure was performed in terms of root mean square error with respect to the noise level as well as the distance between the microphone loudspeaker setup. Two experiments were performed, one involving random noise as input signal against Gaussian background noise. Second experiment was done involving random noise as input signal against ego noise of a drone, and this ego noise of the drone was obtained from the Dragon database. In the first experiment, we tested the performance of our proposed method uh, against white Gaussian background noise. As seen in figure 1a, the proposed method gives low estimation error for SNRs or signal to noise ratios of above minus 15 dB for distances between 0.1 meter and 1.0 meters, whereas for 1b, the SNR or the performance was uh, above minus 10 dB. And in figure 1, the background noise was white Gaussian. In figure 2, the background noise was the ego noise of the drone. In the second experiment, we have done the TOA estimation of the proposed method against the background noise, which was white Gaussian, and the background noise, which was just the ego noise of the drone taken by Dragon database. Now, in the TOA estimation, you can see that in figure B, the time of arrival estimator starts to break down at minus 10 dB when increasing the distance above 1 meter. These observations are expected because the local signal to noise ratio decreases as the distance of the proposed microphone loudspeaker setup is increased against the wall. Moreover, similar behavior will be expected across the remaining signal to noise values if we evaluate the estimator beyond 2 meters, as you can see. Another experiment was conducted, and in this experiment, we were interested in comparing the performance of our nonlinear least square estimator against peak picking algorithm. As you can see, our nonlinear least square estimator performs better when compared to peak picking algorithm, and our nonlinear least square estimator also works uh, also have good performance when the SNR level is at minus 10 dB compared to peak picking. So this is the end of my presentation. Thank you for listening. Have a nice day.